Now in this lecture we are going to talk about two important definitions. One is subring and another one is subring criteria. If you recall, we have already seen similar concepts in vector spaces. We have seen the definition of subspace, we have seen subspace criteria. Then in group theory we saw what is a subgroup and then a subgroup criteria. So similar thing holds for subrings as well. So what will be the definition of subring, right? As you can relate it to the definition of subgroup. So directly I will write it down. A non-empty subset, let us call it as S, a non-empty subset S of a ring R plus dot is said to be a subring of R if S plus dot is itself a ring. Okay, this is how you can write, or you can directly write a non-empty subset S of a ring R is said to be a subring of R if S itself is a ring under the binary operations of R. In that case you are not supposed to write this plus and dot. Okay, so instead of this you can simply write R, and instead of this you can write S, and then you can complete if S is itself a ring under the binary operations of R. That will also work, but here already we have mentioned the binary operations, so no need of saying that statement ahead. Now as we know, this is very tedious job. Proving ring is very lengthy. So now if we have to show certain subset of a ring is a subring of it, then we are again supposed to show that it is a ring. So we are supposed to prove that all the 7 properties together with that binary operations, and so it becomes a very lengthy job. So in order to reduce this, there should be some criteria, and we are calling it as a subring criteria. Now let us see what it is. So it says a non-empty subset S of a ring R is said to be a subring of R if and only if, remember it is if and only if, for all AB belongs to S, these two properties are satisfied. First one is AB should belongs to S, and the second one is A minus B should belongs to S. Now what is this subring criteria saying? Let us try to understand. A non-empty subset S of a ring R, this is the assumption that we are assuming, and there are two parts, if and only if. It is a subring of R if and only if these two conditions are satisfied. So the meaning is ki, first of all we'll assume that ki S is a subring of R, and with the help of this we can prove these two properties, and that is simply straightforward, because assuming S is a subring of R, it means that S itself is a ring, right? That is a basic definition. So that will naturally imply that these two properties holds, no issues in that. Now what about the converse one? So in the converse one, assuming S is a non-empty subset of R, together with this just two properties, we will be able to prove that S is a subring of R. S is a subring of R means what? What is actual definition of subring? S is itself a ring. So assuming S is a non-empty subset of R and these two properties, we will be able to prove that S is a ring. Now what is the meaning? We will be able to show S is non-empty. We will be able to show addition and multiplication are binary operations on S, satisfying that 7 properties. We can prove this easily. Remember, we already done this in group theory, so proof is parallel. So here I will not go in details of the proof, maybe I will leave it to you. That's all. Now the question is ki, suppose some set is given to you, set in the sense a ring is given to you and S is a subset of R. This set S is also given. Now the question is show that S is a subring of R. So how you are going to proceed? So first of all, we are supposed to show S is non-empty. If it is already said that S is a subset of R, then that's very good. Otherwise we need to prove S is a subset of R. So first of all we need to show S is non-empty and S is a subset of R, and then we have to prove that these two condition holds for any two elements of S. And if we are able to show this, then we will say that S is actually a subring of R.